Friends and dear colleagues, I am in the stream of my lectures related to the engineering thermodynamics. As of now, I am in module 4, where I am discussing about thermodynamic cycles or the power cycles. In this flow of lectures, before this, I have completed a basic concept of Otto cycle. Otto cycle is a constant volume cycle. In that, a spark plug was used and the inlet is with a mixture of air and the petrol. And it is entering, and when we are compressing, after the compression, we give the spark plug. So the petrol, which is in high temperature and the high pressure, mixed with the air, it is burning or blast is taking place. That gives a very high pressure to the piston, and piston will move downwards. So in this way, the process of front, rear, it is happening, and we have done it. The main problem of that thing is that the burning is taking place at a constant volume. It needs very less time to ignite full petrol. So the diesel, a scientist has thought that why we can't change that burning process. So in this diesel cycle, a constant pressure means it will give some time. Slowly it has to burn. Then only the burning will take place. In this way, this cycle was designed. So in today's topic, I am going to discuss about introduction to diesel cycle. Why this diesel cycle? Then PV and the TS diagram of diesel cycle. Why constant volume heat rejection in Otto and diesel cycle both? But if you see that the heat addition is constant pressure in diesel, but in Otto cycle it is a constant volume heat addition. So why it is difference? Why we can't make the heat addition at a constant pressure in diesel? Why we have not made a constant pressure heat rejection also? Okay, these things we will be discussing in my next slides. Why does heat addition happen at a constant pressure in diesel cycle? Efficiency of the diesel cycle, we will be deriving the equation just like we have done for the Otto cycle. So revision of the last class topic. So in this we have seen the power cycle. So the power cycles are used for generating the power. Okay, so we have seen that application for the Otto cycle is your bike, car, aircraft, and many other vehicles. Thermal efficiency also we have find out that neta Otto is equal to 1 minus 1 by R gamma minus 1. This also we have find out. PV and TS diagram we have drawn. This is the PV diagram and this is the TS diagram. So in the PV diagram we have seen this is the 1 to 2. This is the constant volume and it is 2, 3 and 4. So this is the expansion, this is the compression, this is the Q in and this is the Q out. So if you see this one, it is like this. 1, 2, 3 and 4. This we have already completed. Introduction to Otto cycle. These things I have done. So now I will discuss about the diesel cycle. First I will go some historical perspective. Who was there and when it was made. So the diesel cycle was invented by Rudolf Diesel in 1893 and he put forward an idea by which we can attain the higher thermal efficiency with a high compression ratio. So in this, if you see the compression ratio is double of your Otto cycle. So he has thought that how we can develop the high compression ratio, because as much you have the high compression ratio in Otto cycle also, you can increase the efficiency. But we cannot make the high compression ratio as the in diesel engine in Otto cycle, because the petrol and the air is mixed and they are coming and then it is compressed. So if you make the high compression ratio in Otto cycle, the pre-ignition will take place and ignition will not be the proper. So that is why we are not using a high compression ratio for the petrol or the SI engine or Otto cycle. All diesel engine works on this cycle. Diesel is used as a fuel in this cycle as it can be compressed at high compression ratio. It is also known as constant pressure cycle because heat is added in at an constant pressure. So in this constant pressure, we are giving the heat or we are burning the fuel. It has high thermal efficiency and the compression ratio from 11:1 to 22:1. Mostly the average of any diesel engine will work between 14 to 18:1 compression ratio. So compression ratio, I have discussed already that it is V1 by V2, means maximum backward and how much you are compressing. That is called the compression ratio. In the Otto cycle, we have 6:1 to 10:1. So your diesel cycle is nearly double of the petrol engine or the Otto cycle. That is the R is more. So the lower compression ratio in Otto cycles is due to the reason that increasing the compression ratio will result in hot spot in cylinder that will lead to a pre-ignition and the knocking. So in this Otto cycle, this knocking will happen, means pre-ignition. I told you that if your high compression ratio, the temperature will be very high, your petrol may burn. So we are not using for diesel engine, we are using the diesel, not the petrol. If you fill the diesel in your, if you fill the petrol in your diesel vehicle, this type of problem may happen. That is why we have to ensure that in the petrol pump, make sure that if it is the diesel vehicle, you put the diesel. If it is a petrol vehicle, you put the petrol. Because someone unknown person, if you are driving a car, the same model may have one diesel vehicle, another may have the petrol vehicle. So make sure that you are using the correct fuel. Otherwise, it will create a lot of problem after that. Oh, why the diesel cycle? So, steam engine used a lot of coal, were very expensive and extremely inefficient. So, I have shown the Rankine cycle. In this Rankine cycle, we have the boiler, and these boilers are heated by the burning of the coal or firewood and other things. So it is very extremely costly also, and also a lot of fuel is burned and a lot of pollution is also in environment. It is done. Big companies could afford them, while little business were struggling to keep up. By studying the thermodynamics, Diesel found he could make a smaller internal combustion engine that would convert all heat into work. Otto cycle engine was having less compression ratio, so need to have a high compression ratio to get more work done. So PV diagram of this diesel cycle here. So PV and the TS diagram. So here 1 and 2, it is a adiabatic or the isentropic compression. 2 to 3, as you can see, it is pressure is constant. If you see the Otto cycle, it is a vertical line like this. But here we have the horizontal line 2 to 3. It is called the constant pressure heat addition. Here the Q in is given. 3 to 4 is a isentropic expansion. So it is expansion is taking place, and 4 to 1 is constant volume heat rejection. So 4 to 1 is same everywhere. 1 to 2 is also same. Only 3 to 4 is different between Otto cycle and the diesel cycle. So if you see in TS diagram, so this 1 and 2 is a heat. This is the isentropic compression. The compression is done. Now 2 to 3 is a constant pressure heat addition. 3 to 4 is isentropic expansion, and 4 to 1 is a constant volume heat rejection. So this you can see, this is the constant pressure and this is the C is equal to constant and here V is equal to constant. If you see in the TS diagram, the slope of this thing is higher than the slope of 2, 3. So this is 4, 1 is a constant volume. So if you start from one point, so this is the V is equal to constant and this is the C is equal, P is equal to constant. P is equal to constant. So the slope of this thing is high. So like this we have to make the diagram. In this 4 to 1 heat is rejected. So if you see this 1 and 2, it is S1 is equal to S2, and for 3 and 4, S3 is equal to S4. Your entropy, change in entropy will be 0 in this. Here if you see this V1 is equal to V4, here it is a V3 and here is a V2. So here we can see that the compression ratio is equal to V1 by V2 or V4 by V2. And here one more thing, from 2 to 3, it is called the cutoff ratio. V3 by V2 is equal to, it is called the cutoff ratio, that we will be discussing in next slide. Oh, why does heat addition happen at constant pressure in diesel cycle? So this we can see the reason why we have chosen that heat addition should be at a constant pressure. The reason for constant pressure heat addition in a diesel cycle is that when the fuel is injected into the compressed air inside the cylinder, question of maintaining a constant volume is vanishes. So if we are giving the constant pressure like this, you get some time. But for the constant volume, it should burn very fast, like a explosion. So that will give a huge amount of jerk and huge amount of problems. We are adding more volume and igniting the mixture as heat addition. Hence, a constant volume is not possible. So these are the two aspects of this thing. That is why we are making the constant pressure. So the first case is, it gives the sufficient time to burn. So if it is a constant volume, diesel has got very thick. It will take more time than the petrol. So diesel was is also cheaper than the petrol. So diesel has diesel cycle was made for the better performance and less cost and cost effective issues. Now, why constant volume heat rejection in Otto and the diesel cycle? If you see here, in both the cycle, if you see here, this is the Otto cycle and this is the diesel cycle. So in this 1 to 2 is your 1 to 2 is a compression. Then 2 to 3 is a heat addition, that is Q in. 3 to 4 is a expansion and 4 to 1 is constant volume heat rejection. So if you see here, if I want to make a constant pressure heat reduction, then this expansion has to go from here to here in the same line, straight line up to here. So initially your piston size is this much, cylinder size is this much, but if you want that, you should go a constant pressure from here to here, this much size of cylinder has to be increased. This much size of cylinder has to be increased. So this is not so advantageous. So in a Otto cycle also and the diesel also, in both the cycle or even in the dual cycle also, we are using the constant volume heat rejection, not the constant pressure heat rejection. Same thing can happen here also. If you see, this much is also here also, this much size of your cylinder will increase. To avoid that, we use this process, that is the constant volume heat rejection. So that is the benefit of doing the constant volume heat rejection. Now we will see here that efficiency of the, okay, so we will find out the same way as we have done for the Otto cycle, the efficiency analysis of the diesel cycle. We will see here that the diesel cycle is also known as a constant pressure heat addition cycle or the constant pressure ignition CI engine. Constant pressure ignition engine. And the Otto cycle is known as the SI engine. SI means spark ignition. Spark ignition engine. Okay, but here it is a constant pressure. So if you see here the diagram here is a 1 to 2. 1 to 2 is a isentropic compression. 2 to 3 is isobaric heat addition. 3 to 4 is isentropic expansion, and 4 to 1 is isochoric heat rejection. If you see this process, 1 to 2 is a isentropic compression. 2 to 3 is heat addition, so temperature is increased. 3 to 4 is this out, and 4 to 1 is in. This is the heat rejection. So same way we will just see that heat added in this is 2, 3 is Cp, T3 minus T2, and heat rejected is here Cv, T4 minus T1. So efficiency of this diesel cycle, eta D is equal to net work by heat supplied. Net work is how much? Cp T3 minus T2 minus Cv T4 minus T1 divided by Cp T3 minus T1. So if I divide this thing, this will be 1 minus Cv by Cp T4 minus T1 by T3 minus T2. But we know that Cp by Cv is equal to gamma. So here we can write 1 by gamma, 1 minus 1 by gamma, T4 minus T1 by T3 minus T2. So same way which we have seen in the last, same T4 minus T1 has come in this also. So here we know that gamma is equal to Cp by Cv, and also the compression ratio R is equal to V1 by V2. Next is the cutoff ratio, it is called the rho. It is V3 by V2. Just you can see here the fuel is cut off and here the fuel has started. So this V3 by V2 is equal to cutoff ratio, and it is a rho. Now expansion ratio is from V4 to V3. So expansion is from here to here. So this is the high value. So V4 is divided by V3. We cannot write V3 by V4 because the value of ratio should be more than 1. So the higher value or the high quantity should be on the top and in the numerator, and the low value should be at the denominator. So we are writing RE, and here we can write RC. Anything, both are same. Okay, so this we will be discussing here. So here we got 1 by 1 minus gamma, T4 minus T1 divided by T3 minus T1. Now we have to relate. Now find the relation by using the isentropic process 1 and 2. So we can see that T2 by T1 is equal to V1 by V2 to the power gamma minus 1. So here V1 by V2 is equal to R, that is the compression ratio, gamma minus 1. So T2 is equal to T1 R gamma minus 1. So we have got the T2 with respect to the T1. Now we will find out the T3 and T4 the same way. So now the process, constant pressure process 2 and 3. So this, we know that this rho is equal to V3 by V2. So now T3 by T2 is equal to V3 by V2 is equal to rho. So this T3 is equal to T2 into rho. Now from this equation, we will put this value of T2 in this. So here T3 will be T1 R to the power gamma minus 1 into rho. This we will see in the next slide. So here we can see that T3 is equal to T2 into rho, but we know that T2 is equal to T1 R to the power gamma minus 1. So we will get T3 is equal to T1 R to the power gamma minus 1 into rho. So we have got T2 and the T3. Now we have to find out the T4. So taking the process which is the isentropic that is the 3, 4. So expansion. So we can write that T4 by T3 is equal to V3 by V4 gamma minus 1. So V4 is equal to V1. So we can write that V3 by V1 gamma minus 1. So here if we take V3 by V2 into V2 by V1 gamma minus 1. So V2 by V1 is equal to compression ratio. It is R, and V3 by V2 is equal to rho. So here we got that T4 is equal to T3 rho to the power gamma minus 1. This is the rho gamma minus 1, and here it should be V1 by V2. So here R to the power gamma minus 1. So this is equal to T1 here rho to the power gamma minus 1 by R minus 1. So in place of T3, we can take from here T1 R to the power gamma minus 1 into rho. T1 R to the power gamma minus 1 into gamma into rho gamma minus 1 by R gamma minus 1. So this R gamma minus 1, R gamma minus is cancelled here, and this rho plus 1 and this is cancelled, only here rho to the power gamma. So T4 is equal to T1 rho to the power gamma. So now we got the T2, T3, T4, everything we got. We will put this in the efficiency equation 1. So this diesel is equal to 1 by 1 by gamma T4 minus T1 by T3 minus T2. So 1 by gamma T4 is equal to T1 rho to the power gamma minus T1 divided by T3 is equal to T1 R to the power gamma minus 1 into rho minus T1 R to the power gamma minus 1. So here we can take out this thing from here to here. So we will take out the T1. So here you will get rho to the power gamma minus 1, and here also you take the T1. So you will get here R to the power gamma minus 1 into here rho minus 1. So you will get the this eta is equal to 1 minus 1 by R to the power gamma minus 1 rho to the power gamma minus 1 divided by gamma rho minus 1. So this is the efficiency equation for a diesel cycle. Okay, so in this way, I think it is very easy to calculate your efficiency of any cycle. So we have done with Otto cycle, that is the 1 minus 1 by R to the power gamma minus 1. So if you put the value of rho, that is the cutoff ratio, more, the efficiency will be less. So this rho value should not be very high. It should be, optimum value should be there, then only you will get a better efficiency. But if you compare with Otto cycle, for the same compression ratio, then Otto cycle is better than the diesel cycle. But it is not a wise idea to put the same compression ratio. So we cannot compare with the Otto cycle and the diesel cycle, because the diesel cycle is having very high, mostly double of the compression ratio. So the size, the weight of the diesel cycle is much more than the petrol engine. So in aircrafts and all, we are not using the diesel engine because it is very heavy. It will give a lot of vibration. It needs the water cooling also. If you see the car, the diesel car and all, they need a this cooling mechanism. Okay, so that is to be used for that purpose. So in my next class, I will be discussing about the dual cycle, need of this cycle, PV and the TS diagram, and efficiency of the dual cycle. So there are some disadvantages in the Otto cycle and the diesel cycle as a both. So we should try to avoid, we should try to minimize, because in petrol engine or the Otto cycle, we have to burn the fuel at a constant volume. It is like this in PV diagram. And in the diesel cycle, it is like this. So the dual cycle was a combination of your Otto cycle and the diesel cycle. The advantage of both the cycles are put in one cycle, and that has become the dual cycle. And most of the this diesel engines are using that dual cycle, not exactly what you have learned just now, this diesel cycle. These are the references which I am taking from the PK Nog, Engineering Thermodynamics, Yunus Senegal, Thermodynamics and Engineering Approach. And then I have also taken some NPTEL videos from professors from IIT Kanpur, Dr. Mishra, and so on. Any questions you are welcome to ask. My email is ydwedi@gmail.com. So I also request you to like and subscribe this channel, and also give the comment if you feel that there is any issues in my lecture. So you are welcome to ask. This you can mail me. I will try to reply. Thank you very much for the joining. Please be tuned for my next lecture, and that is about the dual cycle. Till then, goodbye. See you. Shabakh hai.
Like, share and subscribe. Hit the bell icon for more updates.